now simplify, rather than say for example your state of stress is sigma 1 1 1 2 1 3 sigma 2 1 2 2 sigma 2 3 sigma 3 1 3 2 3 3. So this one is equal to sigma 1 1 1 2 1 3 2 2. And of course, this one will be symmetric. So not a problem anymore. Of course, you can put sigma 1 2, sigma 1 3, sigma 2 3. So not a problem. So now, instead of 9 independent stresses, you have now 6 independent stresses. Of course, with plane stress and plane strain assumption, you can further reduce these independent stresses. So initially 9 stresses, then goes to 6 stresses, and then plane strain, plane stress assumption, you further decrease the independent variables. Yes? Now, let's try to prove that to be able to get your principal stresses, you will need to have, or you simply need to take the determinant of that so-called initial stress that we have. So, what do I mean by this one here? So let's look at solving your principal stress. So your principal stress, you have sigma 1, sigma 2, and sigma 3. So meaning that you have a state of stress. Sigma 1 1, 1 2, 1 3. So that is symmetric, right? So this is your state of stress. So to be able now to calculate your principal stress, your determinant of this one here, minus sigma 1 2 sigma 1 3. So the determinant of this one, so these are stresses, must be equal to 0, and then you can calculate the roots of your equation. The 3 roots will be your principal stresses. Sigma 1 will be the highest, sigma 3 will be the lowest, and sigma 2 in between. How do we solve this one? Now there's a definition about traction. So a traction, again, is just by definition. So this traction here, so you have that in your notes, there's a definition by traction there. It's that force normal to the surface. So this equation here, so this one is called the traction. So this can be equal to, by definition, sigma, stress, multiplied by that normal. So this one is a magnitude, while this one will be your direction. So it's a vector. So if you have an I here, so the free index is simply 1, so this one is a vector. So this is the magnitude, and this will be the direction. This is the normal, direction of the normal. So of course, if this one will be in 3D, that will be, say, T1, T2, T3. This will be equal to a magnitude multiplied by N1, N2, and N3. So they are directions. So here they cannot be zeros. another way of rewriting this fraction here. Another way of writing this fraction here will be fraction instead of using the normal stresses or using the principal stresses. You can use the state of stress, sigma ij, and this will be, or let me just put here, sorry, sigma ji and j. So this is a fraction. It can be written using the principal stresses, or it can be written using your, or sorry, this will be an nj. Let me erase that, sorry for that. You can have this one to be EI equal to sigma ji and j. So as you can see, j is a dummy here, so on your left side is I, so that the product here will be an I. Sigma ji and j. So j is a dummy index. You can have k, l, m, n, and o, whatever you want to do. They will be cancelled out anyway. Instead of using the state of stress or the principal stress values, you can use now your state of stress. You can do this one, not a problem. If this one is 3 by 3 and this one is, say, for example, 3 by 1, then you end up with a 3 by 1 for this one here. So take note, these are direction normals, or the direction of the normal, n1, n2, and n3. They cannot be zeros. So what we're going to do now, so we have a fraction here and a fraction here. What we're going to do now is to equate both. So what am I saying here? So read fractions. Pi is equal to Pi. Please follow this one. What's the equation for 1 Pi using the principal stresses, sigma and I? This one is equal to sigma Ji and j. Yes, we have two equations. One using the normal, or one using the principal stress, and one using the complete state of stress. Both will be the same. It's just that you're just representing them in two different languages. Right? So we equate them now. What happens with this one now? Again, just for your information, allow me to write this one. Sigma 1, 1, 1, 2, 1, 3, sigma 1, 2. Yes? So this one, if I write this one is also sigma. You have N1, N2, and N3. So they are basically the same thing. Yeah? So J, so that is J1, sigma 1, N1, N2. So in the meantime, just write them as sigma Gi and G. So in the meantime, let's just write them as sigma Ji and J. So let's do a magic for this one later. Right? So just accept that at the moment. There's a bit of confusion here. Just accept that at the moment. So I have now here sigma ji multiplied by nj minus sigma ni, that is equal to 0. Right? So what do? We take away the normal because they are basically the same, one and the same. But one is nj and the other one is ni. So obviously we need to change one, or we need to put in a multiplier so that this one will be nj, or say for example this one will be ni, but we want to add a multiplier here. What about Kronecker delta? Say Kronecker delta is equal to 1 or 0, yes? So if you multiply it here, then it wouldn't change much, or it wouldn't change anything. So what do I mean by that? Let's look into this one here. Sigma ni. So what happens here is, I can write this one here as sigma multiplied by delta ij. So this one is equal to 1 if I is equal to j. If I is equal to j, this is equal to 1. But this one is ni. This one is equal to 1 if I is equal to j. So here I can write this one to be nj. Sigma n1, n2, n3. If you write this one here, sigma, that is delta ij, let's write it as a 3 by 3 matrix. Delta 1, 1, delta 1, 2, delta 1, 3. Yes? But delta ij, or the Kronecker delta, is equal to 1 if I is equal to j. Yes? So this one is 0, that's 0, 0, oops, okay, that's 1. So that's 1, and this is 0. Yes? So we have an identity matrix. So your delta ij is actually an identity matrix. For 3 by 3, it is a 3 by 3 identity matrix. Yes? Now let's try to prove that this one is equal to that. So this one now is 1, 1, 1. Yeah. 1, 1, 1, 2, or 2, 2, or 3, 3. So j is equal to n1, n2, and n3. So you multiply this one there, you'll definitely get sigma n1, n2, n3. Yes? So you just need a multiplier delta ij. Kronecker delta. So if you put in Kronecker delta here, you can have sigma delta ij nj. So sigma ni can be delta or sigma delta ij and j. So you have proven that already, because we know that your delta ij is an identity matrix. Let me just put it there. So this one is an identity matrix. You put it here, so you will get the same sigma n1, n2, and n3. Still okay so far? So that's why before we started the class, I reviewed you with tensors. So, hope you're okay there. Let's continue a bit. There we go. So we can have now here sigma ji and j. This is now minus sigma ni equal to 0. Just repeating that. So we have now here sigma ji and j minus sigma delta ij and j equal to 0. So now I can take away nj. So I can take out now nj. So here sigma ji minus sigma delta ij nj equal to 0. Yes? This is your normal. Your normal cannot be equal to 0. Your normal directions must not be equal to 0. It should not be 0. So if that is not 0, what should be 0? So this is A multiplied by B. If B cannot be 0, what should be 0? A. Nj must not be equal to 0. Yes? Still alive? Of course, if this one is equal to 0, since this one is an eigenvalue problem, yes, so that the determinant of this one must vanish. Yeah. So again, if you rewrite this one here, say I'm going to write sigma ij 1 1, sigma 1 2, sigma 1 3, 1 2 2 2. Yes, and then of course sigma here. If if I equal to j, 1 equal to 1, so that is now minus sigma. I equal to j, 1 2, I not equal to j, so that is 0. So I equal to j, that is 0. I not equal to j, that is 0. I equal to j minus sigma. And then here, I equal to j, that is minus sigma. So that the determinant of this one must vanish. You get now again the roots of your equation. So either you use the equations that you have, solving the invariants, and then of course determine the values of sigma. I think the equation here, so you can take the determinant of this one. There are many ways of determining the determinant here. So in this case, you can take the determinant, or you can simply write your equation. So in 3D, So that is the case in 3D. So that is I2. Invariant 1, invariant 2, invariant 3. And what are these values? This one is in your notes. Invariant 1 is sigma 1, 1, sigma 2, 2. Yes? Or this can simply be sigma kk or sigma ii. Take note, it's just a dummy index, not a problem. The second invariant, I'm just copying the equations now. Yes, and then finally, your I3 will be the determinant of your state of stress, without, of course, the sigma. And then put it on here, and then you have now a cubic equation. Solve for the roots of the equation. In 2D, so of course we already discussed about plane stress and plane strain. Your equation now to solve for the principal stresses will be a quadratic equation because you only have two roots. So that will be sigma squared minus I1 sigma equal to 0. And then of course I1 is simply sigma 1, 1 plus sigma 2, 2. And then your I2 is sigma 1, 1 sigma 2, 2 minus sigma 1, 2 squared. Okay, so these are just your equations. Of course, nobody's preventing you from taking the determinant, come up with a cubic equation and so on, or quadratic equation, and then solve for the roots of the equation. So that's now algebra. Okay? Do you want to prepare a set of notes, bring to the library so you can just ask the library to print out for you? Yes. And I think it's better that way. I pity you guys. I should just let you go and then print your own. But okay. Actually, in Glasgow, they don't bring these notes to the library. They just give all this. What do you call this one? They just give all these materials online, so students will be doing that. But anyway, since I think you're going to use that during your exams, then I think it will be cheaper if we just ask the library to photocopy copies for you guys. Okay, I'll make some arrangement, and probably before our class on Thursday you will be having a copy. Anybody who printed out already? So let me just summarize what we did today. First is to convince ourselves. So we did a bit of review, all these stresses. Sorry, can we have an hour next meeting extra? I want to make up for the previous weeks that I missed some classes. So I'll send an email before our meeting on Thursday. So can we have an extra hour after our class? I would like to extend now, but I didn't announce it properly, or it's a short notice, so we'll just have it on Thursday, an extra hour. I would like to discuss a bit more, but let me just summarize what we did. So what we did was we had So we had the equilibrium equation, yes? we discussed the equilibrium equation, wherein we take the summation of forces, say along one direction equal to 0, sorry for that. And then what did we come up with this one here? We have now sigma ij, comma I is equal to 0. So here, of course, if you're not very comfortable writing this one, you can have this one as partial sigma ij xi equal to 0. So not a problem. So what I really want by the end of this course is at least you have an understanding of playing with tensors. So the next thing we did was to derive that symmetric relationship of your state of stress, wherein we had summation of moment about a certain point O within your element. This one is equal to 0, and we came up with sigma ij equal to sigma gi. So instead now here of having 9 stresses, from 9 stresses, we were able to reduce this one to 6 independent stresses. So here, as you can see, that 6 stresses, independent stresses. Now, we had plane stress, and then we have plane strain. So plane stress, we discussed that one side is much thinner than the other two, so that we have your stress 3 is equal to 0. So again, your independent stress will be reduced to 3. Similarly, for plane strain, we assume this one that one side is much larger than the other two sides, so that you have now your strain 3 to be equal to 0. So then again, from this assumption that you have now 3 independent stresses. So from 9 initially, it is reduced to 6 because of the principle of symmetry that we were able to convince ourselves that it's true because we derive it based on first principles, so we get 6 stresses. Now, to be able to further simplify this one, we have plane stress where one is much thinner, or one side is much thinner than the other, so that the stress on that plane will be equal to 0. And also we have plane strain wherein one dimension is much bigger than the other two dimensions. We have strain equal to 0. So again, this will be reduced to 3 independent stresses, which makes our analysis now much easier. Of course, after this one, we were also able to, finally, we were able to derive, what was that again? So again, from first principles, we were able to derive this equation, which allows us now to solve for the principal stresses. Can I add? Yes, can I add here? Let me just add von Mises stress, which we will study later, and will be very useful. So this one can be equal to, so once you have the state of stress, you can solve this one to be sigma 1 minus sigma 2 squared. So that's the von Mises. This is the von Mises stress. So we have the principal stresses, and We also have another one for ductile material. We have the von Mises stress. So just let me write the equation. So this can also be very useful. So I hope you can see this one. Yeah, that's plus 6, sigma 2 3 squared, sigma 3 1 squared, sigma 1 2 squared. So these are the shear terms, and these are the normal stresses. Of course, this can also be equivalent if, sorry, that's 1 all over square root of 2. So this one can also be solved using the principal stresses. 1 all over square root of 2. So that is now sigma 1 minus sigma 2 squared. So the principal stresses, if you have, or you're using your principal stress for failure theories, this one is only applicable for brittle materials. While for von Mises stress, you can apply this one for ductile materials. Of course, we will also use the von Mises a lot for the when we go to theory of plasticity. So we haven't discussed anything about solutions yet. So I'm hoping that we can have some discussions next meeting, solve some problems. Okay. So I hope that you try to go over your notes again. I'll bring the notes to the library to be printed out. Hopefully it will be available before you go to class. So it will be available by Wednesday. I'll try to make it available by Wednesday.